You ready to begin? All right. Okay. Good afternoon, everyone. Welcome again for the Tuesday seminar series at the Warsaw University Astronomical Observatory. And today, our guest is Elena Pancino from INAF in Italy. Elena obtained her PhD in Padova, and then she was a postdoc at ISO, and then in Bologna for many, many years, where actually she was working heavily, she was heavily involved in development of Gaia data processing. And this is how we met actually many years ago. And then also we've been working together on Loiano Observatory, and some of our students from Warsaw were actually hosted by Elena herself in Loiano while they were observing some targets there. So we wanted to thank you, Elena, for this. These were great times. And now she's a professor at Arcetri Observatory near Florence, and we just discussed that this is the resting place of Galileo. So there is a lot of history in that very beautiful place. And Elena received recently an advanced ERC grant, and she's going to tell us more about it. So Elena, please.
Thank you, Łukasz. Thank you for the invitation and for the introduction and for the opportunity to present my project. As I was saying, the project has just started. It is called StarDance, the non-canonical evolution of stars in clusters. And because the project has just started, there is no striking new result yet. So I will just introduce the concept. Let me start with the star clusters, which is the environment in which most of the project will take place. As those of you working in the field know, star clusters are one of our best astrophysical laboratories in the sense that they are made of many stars with similar properties, distance, metallicity, reddening, age, and therefore they are the ideal test benches for our stellar evolution models, right? And we can use them as laboratory also for stellar dynamics, one of the best places to put to the test dynamical principles. And once we build the stellar evolution models and we calibrate them on our clusters, they become the models, our stellar clocks that we can use to define the age scale of the universe, at least the part of the universe closest to us, by measuring ages of stars using the calibrated models. We can also use star clusters as templates to reconstruct more complex stellar aggregates, such as galaxies. And we can do this by creating synthetic color magnitude diagrams to study the star formation history, for example, of the Magellanic Clouds, the Milky Way halo, and so on. Or we can build synthetic spectra to study more distant galaxies where we cannot resolve the individual stars. And finally, star clusters, being much brighter than a single star, they appear as very bright objects in distant galaxies, and so they can be used as test particles, even in our own Milky Way, to study the potential of the Milky Way, to consolidate the extragalactic distance scale. They can also be used as standard candles in many ways, and so on and so forth. So they are fundamental objects, even if you don't study specifically stars, okay? Even if you study galaxies and the like. However, this tool is somewhat broken because there are two main problems. The first one is that we are not sure of how star clusters form. We do not know, especially the globular clusters, and we cannot fully explain their stellar content, especially when it comes to non-canonical populations. So the two elephants in the room have names. The first elephant in the room is called multiple populations in globular clusters specifically. I will describe a bit more about this, but just it is a very old problem. We discovered it in the late 70s of the previous century, and they manifest themselves as element variations among stars in cluster, which should be twins born together, so they should be identical to each other, but they are not, especially as far as light elements go. And all of the attempts we made at explaining this, they don't work. So far, we've been focusing on stellar generations, but if there are different stellar generations in globular clusters, this means that old objects at high redshifts form in a very different way compared to the clusters that are forming today. So we don't know how does it work? How does star formation work at high and low redshift in the past and in the present? The second elephant in the room is called non-canonical stellar populations. And by these, I mean all populations in star clusters, but also outside of them, which are not made of single undisturbed stars. So I'm talking about mostly populations that are thought to be the result of binary interactions, such as blue stragglers, red stragglers, yellow stragglers. They come in every color. Hot sub-dwarfs and extended horizontal branches, lithium-rich stars, extended main sequence turn-offs, and so on and so forth. They are visible in all types of clusters and in the field as well. What is the problem is that we cannot really explain all of these populations in detail. And if this is true, it means that we cannot model them in detail. And if we cannot model them in details, when we adjust or calibrate our stellar models on the clusters, for example, to calibrate a stellar clock, we may end up calibrating our stellar clocks in the wrong way. And we may have mistakes in the age scale of the universe up to 10%, or according to some author, even 50%. So let me start by going a bit more in depth about the multiple populations in globular clusters. What are they? As I said, they were discovered a long time ago. And the first manifestation of this phenomenon was a variation of the abundance of light elements among the stars in a single cluster. Okay, this was called at the time anticorrelations or anomalies. And you can see here the three main anticorrelation planes that have been studied across the years. The first is the carbon-nitrogen anticorrelation plane. The second, do you see my cursor?
Yes.
Okay. So the second is the sodium-oxygen anticorrelation, and the third one is magnesium-aluminum anticorrelation, right? So in these plots, you see this big red circle is where the halo stars of similar properties of globular clusters lie. So these are the normal stars, while all of the stars outside of these circles, here, here, and here, they are globular cluster stars with an anomalous chemistry. And you can see that these anomalous stars have a higher amount, for example, of nitrogen and a lower amount of carbon than the normal stars. This is why we talk about anticorrelations. In this plot, you have stars from different globular clusters combined in the same plot, just to give you the idea. But even if you look at clusters one by one, you do see these variations, and they are not expected at all. One important thing to consider is that iron, peak, and heavy elements, they do not vary among stars in globular clusters or in any other cluster that we know, except for some very peculiar clusters, which are about 20% of the total known clusters, which we will set aside for the moment because it's already complicated enough. And we want to start understanding what's going on. Now, where does this chemistry come from? It was immediately recognized, like no more than 10 years after the first discoveries, that this chemistry was compatible with the CNO cycle equilibrium abundances. Now, the CNO cycle is the way in which you burn hydrogen to transform it into helium using all of these light elements as catalysts, meaning that you use them and then you free them again. However, in the complex reaction network, some reactions are faster and some are slower, which means that some elements are accumulated and some others are destroyed. And when equilibrium is reached, you have an alteration of the abundances of these elements. And in particular, for example, nitrogen is enhanced while carbon, oxygen, and fluorine are consumed. Now, where does this happen? Now, the CNO cycle, at least this portion of the CNO cycle, happens in the cores of main sequence stars that are massive enough. But it also happens in the shells of red giants, both in the first and second ascent to the red giant branch, at all masses, at the hot bottom, let's say, of the hydrogen burning shell. Now, when temperature is high enough, there are other reactions that become more and more efficient and they activate, and these are the neon-sodium cycle and the magnesium-aluminum cycle. Now, because the temperature at which these cycles occur is higher, the mass of the star that can activate them becomes higher. So for the neon-sodium cycle, for example, you need main sequence stars of at least 20 solar masses to be able to activate it, right? In the shells of red giant branch stars, which are hot but not so much, you need at least 1.5 solar masses, and AGB stars can do it at all masses. But if you move now to the magnesium-aluminum cycle, you need really, really very massive stars, like 60 solar masses or more, and even then, you need to alter the reaction rates, which are uncertain, of some of the reactions in this chain here, to be able to reproduce the observed chemistry. So it's very difficult. And it appears that the only stars that are really able to do it are AGB stars, okay? Of massive AGB stars, meaning at least 5 solar masses. So now we have the sources of this type of chemistry. What we're looking for is a way to make this chemistry go on the stars that we observe today, right? Because some of them, I will show you later, they are not able to activate these reactions inside them. If you have a globular cluster, you have 0.8 solar mass stars, so a very low mass, which is not able to activate this chemistry in all phases. So later, let's say at the turn of the century approximately, I'm showing here a result from my own PhD thesis. The first evidence of these type of multiple sequences in color magnitude diagrams comes from this paper by Lee et al. In 1999. And then later with HST photometry, we have fantastic diagrams like the one you can see here. What you see here is the main sequence. I believe it is NGC 2808, in which you see 3 separate main sequences, only with HST photometry. So in the color magnitude diagram, instead of seeing something similar to an isochron, you see multiple sequences. And this is why the name multiple populations took place and started to be used by everyone. Now, the explanation on why the chemistry that we saw before should produce multiple sequences, as we are seeing now, goes both in the structure of the star and in the molecular bands that you see in the atmosphere of the star. So for the molecular bands, you see here a figure from a paper by Sbordone and collaborators. You have 2 synthetic spectra here. The black one is a normal halo star, and the red one, a star in a globular cluster with altered chemistry. And you see that the molecular bands of CN and NH as well, and CH, are deep enough to alter the blue colors in this range where you have the U and B photometric passbands in the Johnson-Cron-Cousins system. The presence of these deep molecular bands really changes the magnitude of a star seen in these filters. And concerning the structure of the star, because we imagine that this chemistry is produced by the hot hydrogen burning, it means that these stars should have a chemistry altered also in their helium abundance, right? And the helium abundance changes the structure of the star. It makes it more compact, hotter, everything else being equal. And so the structure of the star changes. And so we see multiple sequences. And luckily, the fact that stars move away from the canonical sequences allows us to create color plots, like the one that you see here, for example, which are called the chromosome maps, and they were first employed by Milone and collaborators in 2017, where you can basically create a 2-dimensional plane of a color combination which maximizes the variation in nitrogen, or let's say the impact that the nitrogen variation has on the color, and the impact that the helium variation has. So you can divide stars in first population and second population. which is normal stars in the halo that I showed you before in that big circle, and all the other stars, and even to classify subgroups, like you see in this plot. Okay, so was the framework for the multiple populations. So where do we stand now? Basically, we see these abundance variations in all phases. So we see them in the horizontal branch, asymptotic branch, red giant branch, subgiant branch, and main sequence. Okay, now in this scale, you don't see any multiple sequence at all. It's just to show you a color magnitude diagram for those of you who are not experts in stellar evolution. So these are different evolutionary sequences where in very few of these phases, the stars are able to activate that reaction network that I showed before within themselves. So one thing on which everybody agrees is that this chemistry must come from outside of the stars that we observe today, right? And this is the first point. Now, the second point is that because we see it in every phase, it means that the pollution that the star has suffered is substantial. So a large portion of the star, if not the entire star, must have been polluted to be able to survive all of the mixing episodes and the structural changes that the star undergoes during its evolution. And also, because we see them even in the very beginning of the main sequence, so in those stars which have just started reaching the main sequence now, we can say that the star must have been polluted when it formed already. So the stars form from polluted gas. So these two observational facts led to these two interpretation pillars, if you wish, which naturally lead to generational scenarios, which are the most explored to explain what we observe. Now, generational scenarios are scenarios in which a first generation of normal stars, like the stars that you see in the Milky Way halo, eject the gas polluted by the CNO cycle chemistry, and this gas is collected at the center of the star cluster to form a second generation of stars, right? So this should happen only in globular clusters and not in open clusters, for example. And it has to happen fast because we know that massive clusters outside of the Milky Way get rid of their natal gas rather soon, let's say in a few million years since their birth. And also, however, we need the time to collect the gas, condense it, and form new stars out of it. So it's a really tight spot that we're looking for. Now, once you have this scenario, which is not a model, but just a logical sequence of events in your head, then you can look for the polluters. So who are the stars which are able to eject the gas polluted by that chemistry, by the CNO chemistry, into the cluster? So you need a star that is able to produce a wind of some sort. And so the most explored, I'm summarizing here a few of the most explored ideas. One is that of the fast rotating massive stars. So these stars are massive stars. They activate CNO cycle burning at hot temperatures in the center, and they often rotate fast. So they have a decretion disk, and then they can give back through a mechanical wind all of these CNO products into the environment. And there are even images of these massive stars forming new stars in their disk. So that was one scenario. The problem here is that the magnesium-aluminum anticorrelation is difficult to explain. Then massive AGB stars, they have this double shell structure. So helium burning shell close to the core and a hydrogen burning shell above it. And here there is a rich set of nuclear reactions that is taking place. And we know it has been also proven observationally that we are on the right track in imagining what happens within the stars. And they have slow winds that are slow enough not to escape the potential well of the cluster. And then there are also massive interacting binaries. This was a scenario that was produced in 2009. And in massive interacting binaries can lose gas through the outer Lagrangian point and give this gas back to the cluster. Or there is this very fancy scenario in which you have a supermassive star, which is forming simultaneously with the cluster and polluting the environment from which the cluster stars form. And of course, we never observed a supermassive star, but they are theoretically predicted. So what is the problem with these generational scenarios? Why are we not satisfied? We are not satisfied because there are, if you look at this, at these plots here, there are as many stars with anomalous chemistry as there are normal stars, if not more, like in this case. Now, how can you create a second generation which contains more stars than the first generation which gave birth to them? This is called the mass budget problem. So people are working on this, imagining that you lose a certain type of stars, accrete some others, and so on and so forth. But it's very difficult to figure that out. Also, the chemistry that we observe has a range. It's not just normal and polluted with nothing in between. So we need to dilute that chemistry to obtain exactly the numbers quantitatively that we observe. And to dilute it with primordial gas, you need to accrete a lot of primordial gas on the cluster, which, however, has a shallow potential well. So you have a gas dilution problem, but also a gas retention problem, because the cluster, how can it retain the gas long enough to form new stars? It has a small potential well. Okay, all of these problems are discussed in details in these two papers, review papers, which are super interesting if you're interested. Now, while some people try to solve these problems, some other people, few, like including myself, try to change perspective and use a lateral thinking to go out of the mainstream and to find possibly original solutions that might work. So before I go to another solution, let me show you where this phenomenon happens. So you see a plot here of total cluster luminosity versus age. And the cluster luminosity is a proxy for the cluster mass. So you see the mass lines here. So initially, the phenomenon was only seen in Milky Way globular clusters. So the red symbols here. The empty symbols are the ones that in 2012, they were not explored yet. Some dubious cases here. And the crosses are the clusters which do not have anticorrelations or multiple populations. So it looks like there is a threshold in mass of the order of 10 to the 4 solar masses, below which the phenomenon doesn't happen anymore. What about age? It looks like from 2012 that there is also an age limit, but this was unclear. One interesting thing is that all clusters, all globular clusters in the local universe show the multiple populations. So we saw it in the Magellanic Clouds, in dwarf galaxies, and then there are a few stars with the anomalous chemistry in the halo and bulge of the Milky Way, but they are compatible with being escaped from globular clusters. However, more recently, people have been exploring Magellanic Cloud clusters, which are younger but still massive. So we are still above the mass threshold that we believe switches off the phenomenon. But we found the anomalies even in clusters as young as 2 gigayears. So now this becomes problematic because open clusters of 2 gigayears don't show the multiple populations, but those intermediate clusters that are not present in the Milky Way, they are only seen in the Magellanic Clouds, which are massive enough, even if they're young, they show the problem. So we started by a phenomenon confined to globular clusters, and we're now slowly moving to a phenomenon that appears everywhere, but with different proportions, of course. Now, what gave me the idea behind my project is that I found a chemistry that is in some ways reminiscent of the one of globular clusters in 5 super famous open clusters: the Pleiades, Ursa Major, Coma Berenices, the Hyades, and Praesepe. What you see in these plots is the sodium, oxygen, and magnesium abundance of open cluster stars in the turn-off region of these clusters, which are the colored symbols, compared with the gray dots in the background, which is what you see in globular clusters, and the red circle, which is what you see in all other places. So the normal disk chemistry, now we're comparing disk with halo, so there is an offset in the alpha elements, but In this big circle, you have all of the normal open cluster stars. So all of the red giants in open clusters have solar abundance and abundance ratios of these elements. But the stars close to the main sequence turn-off, which sometimes rotate fast and they are hot, they have a strange chemistry which changes from cluster to cluster. But if you look at Coma Berenices, or even at the Hyades, you can see stars with high sodium, and you see the error bar, so it's as high as in globular clusters, and low magnesium, for example, or low oxygen. So this is a chemistry that is still compatible with that of the CNO cycle, and we're seeing it in objects that are much younger than 2 giga-years, down to 100 million years. So this chemistry is everywhere. But apart from all of the implications and complications of this result that we're still trying to understand, what one can derive from these plots is that if the red giant branch stars in open clusters have normal chemistry, and the main sequence stars in open clusters have a strange chemistry that reminds, to a certain extent, that of globular clusters, then this chemistry can be transient. Okay, and this is like lighting up a light bulb, because immediately, if this is transient and we go back and revisit our paradigm, you remember, now we see the abundance variations in all phases in globulars. We see it in stars that cannot produce it themselves, the same in open clusters. Now, the chemistry must come from outside, that's fine. But instead of looking for a chemistry that might survive all of the evolutionary phases, we can also look for a scenario in which it changes with time. Okay, so only now we're observing the cluster and we see that chemistry. But in the past, maybe it wasn't like this. Or in the future, it will not be like this anymore. So we can relax one constraint that was implicitly assumed by all scenarios and attempts so far, which is basically that we can start for the first time to imagine a mechanism that acts at all evolutionary phases. Okay, and so you have stars that can become polluted and maybe go back to normal later. And so maybe some stars were polluted at birth and some were polluted later. Some stars will have the chemistry that lasts for a long time, some others for a short time. And what we observe is a statistical superposition of all of the stars that now are polluted in globular clusters. Okay. Now, if you think this way, the mechanism could work. What could be a mechanism that works like this? And here it comes to my hypothesis, which is interacting binaries can. Okay, there are interacting binaries of all types. We have stars exchanging mass through Roche-Lobe overflow. We have stars focusing the wind of the donor through the Roche-Lobe to the Lagrangian points, basically. We have also stars that go through common envelope and exchange mass in various ways and then rearrange later, either by merging or becoming binaries, but perhaps with a different chemistry. And so once we observe stars with a strange chemistry in globular clusters, we may be observing either a stripped donor, which exposes the layers where the CNO cycle is taking place, or a polluted accretor, which has accreted gas from a companion polluted by the CNO cycle and mixed with the diluting material in the envelope. And the star can be heavily polluted depending on the metallicity, evolutionary phase, age, and everything. It can be heavily polluted, so in a thick layer or in a thin layer. And so the chemistry can be either persistent or transient, depending, okay? And this is the hypothesis that I need to test with the European funds that I received. So the funds are to test this hypothesis. So in this hypothesis, each star has its own story. It can have a different polluter. It can be polluted in a different moment or evolutionary stage. The pollution, or let's say the mass transfer event, might have had a different duration. And as well, the strange chemistry might have a different duration in time. And this depends on the mass transfer history that the stars have had in their past. Combined all of the stars in the cluster in one statistical snapshot of everything that happened in this regard. Now, how could this help overcome the three main difficulties that I mentioned? There are other difficulties, of course, and there is a lot of work to do. But for the mass budget problem, if you only pollute part of the star, you alleviate the amount of mass that you need to produce such a population. And of course, both donors and accretors can show a different chemistry. And therefore, this alleviates even more the mass budget problem. With the same mass, you pollute two stars, basically, and only a part of these two stars. For the gas dilution problem, the envelope of the stars, if the star is an accretor, can act as a source of the dilution material. And the degree of peeling of the donor acts as a source of dilution material, because if you reach the place where the full CNO was taking place, then you will have the full CNO equilibrium abundances. But if you only peel higher portions, you only have a smaller amount of these elements. And finally, you do not need the cluster to be able to retain the gas to form a new generation. What counts here is the potential well of the binary star and not of the entire cluster. And that is enough, because we know through the Lagrangian point it is possible to exchange mass. So the hypothesis is there. We need to consolidate it, test it, build a scenario around it, and pave the way for a model of the formation of these populations. Now, all polluters that we discussed so far are good. So the carbon-nitrogen anticorrelation can be done by almost any star that is in the red giant branch and any star that is on the main sequence with a mass above 1.3 solar masses approximately. So that's fine. And sodium oxygen requires a bit more mass. And the magnesium aluminum needs massive AGB stars. And there are also stars with S-process pollution and high C plus N plus O sum, and these could be produced by low mass AGB stars. So we can combine different polluters and make them act at different times statistically. Now, the red giant branch stars are a new polluter that was not considered in generational scenarios because their chemistry remains within the star. So there is no way for these stars to eject polluted gas to contribute to a new generation of stars. But if you put these stars in a binary star, then you can peel off the outer layers until you reach regions that are polluted by the hot reactions taking place at the bottom of the hydrogen burning shell. So if they are in a binary, they can be peeled off and produce the chemistry. So we have additional polluters compared to generational scenarios. Another interesting fact is that if the donor star rotates fast for some reason, because it's a bit more massive, so perhaps magnetic braking was not very efficient on the main sequence, and so the donor may have a different evolution of its angular momentum, then the internal stratification of the elements is different. And this adds variety to the types of chemistry that you can obtain, and also enhances some of the chemistry that you can obtain, because it makes the gas migrate, we think, outwards with a strange chemistry towards closer to the surface of the star, let's say. Now, another consideration is that binary stars are plenty. Now, if we look at a normal cluster like M67, it is the archetypical open cluster. It is made of solar twins, basically, to make it, just to place this in our reference frame. It's just made of stars like the sun, especially those at the turn off or in the upper main sequence. They are solar metallicity. They are not as dense as globular clusters. M67 does not show the chemistry of multiple populations, at least not where we have looked at. We have carefully avoided the binary byproducts because they are difficult to analyze. But in the normal stars, it is normal. But we do see, okay, a binary sequence. If you see my cursor parallel to the main sequence, we see a hint of an extended main sequence turn off, which becomes broader as the stars are brighter. We do see a binary sequence also up here. We have yellow stragglers, blue stragglers, sub-subgiants, and even blue lurkers, which are fast rotating stars in the main sequence. So a normal cluster like this, which is not exceptional, is not comparable to a globular cluster, already has a very rich zoo of binaries and binary byproducts. So binaries are there. So far, we avoided them in determining the chemistry because they are difficult to analyze. And so we do not know what is their chemistry, right? And so this is one of the things that we can do, is to study the chemistry of these binary byproducts and see where the connection can be made with multiple populations or with that type of chemistry. And the idea is that the more massive the cluster is, the more dynamical interactions are favored, including three-body encounters, which can make binaries tighter. And so it can stimulate, like in globular clusters environments, you have more of these strange stars. In open clusters, you have already several. And in the field, you have very few. So binaries are plenty, and it does make sense to deepen the study of these binaries and binary byproducts. So how to test it? So the idea is very simple. Every time you have the right type of binary, which is still unknown in details for the moment, you should have that chemistry. So every binary that is able to produce that chemistry will produce it, regardless of the environment. What changes is the number of objects that you have in a globular cluster compared to an open cluster compared to the field. And also metallicity does play a role because of the structure of the star and how well the star can retain this chemistry. So in metal poor and massive clusters, you have more binary interactions, more stellar interactions in general. You should have more multiple populations, but multiple populations should be everywhere. So to test this, what I plan to do is to assemble a sample of many stars in different environments of different types of binaries, of which we measure the chemistry, and we see how the chemistry works out. And of course, we will also explore this theoretically a little bit more to identify the parts of the parameter space of interacting binaries which are more promising. And we want everything to work well, not just, I don't know, this binary reproduce the carbon-nitrogen anticorrelation, I'm happy. I want also something like, it has to reproduce also the sodium-oxygen, magnesium-aluminum, binary fractions, binary distribution, kinematics, and the fraction across clusters of different properties. So it has to be done in a way that is self-consistent. So it's a meta-study, if you like. So the core of this project is, in fact, to study spectra of stars to determine their chemistry and use chemistry to identify the nuclear production sites at the most likely type of binary that you can have. Now, with this, I'm almost there. So I put here my conclusions. So there's a new hypothesis to explain a phenomenon that is unexplained, let's say, since decades, which involves the study of interacting binaries and non-canonical stellar populations in general, like lithium-rich stars as well, which are objects that deserve to be studied per se, not only to explain multiple populations, but just to understand non-canonical stellar evolution. So I will build a database of interacting and rotating stars in different environments and measure their chemistry. And this should help a larger set of communities, for example, people studying with astroseismology, the stellar rotation, having chemical information on what's on the surface should help, right? And characterizing many binaries, that should help many different fields of research. So keep an eye, if you're interested in this type of science, of course, keep an eye on our results and databases. If you are looking for a postdoc, I have opened a position right now. So in the next 2 weeks, it's the deadline, I think. So consider this as well. Consider coming to Italy, working with us. And I thank you for your attention. But before letting you go, I would like to advertise this meeting in Florence. Again, the deadline for the abstract submission is near. So if you're interested, please do not hesitate and submit an abstract. It is to celebrate the career of Peter Stetson, who also has a large database of epoch photometry for star clusters. So it should be useful for the project that I described so far. But he worked on different fields like the age scale of the universe and the like. So the topics are resolved stellar populations in general, and the Milky Way and the local group, and variable stars and so on. So thank you again. I hope I didn't go over time. No, not yet. Good.
Excellent. Thank you very much, Elena. I'll do the clapping on behalf of everyone.
Thank you.
Thank you for a very interesting topic. Are there questions? You can raise your hand on Zoom and then you can ask it yourself. The topic of open clusters is close to the heart of many of us in the Warsaw Observatory. We've been doing, one of my first ever observations were of open clusters with Grzegorz Paczyński. There's a question from Paweł, please.
Yes, thank you very much for a very nice talk. A lot of informations, of interesting things. But I would like to ask you, are you using any surveys like Gaia ESO survey of metal-rich, metal pool stars, or Gaia benchmark stars that can be used for a comparison, for example?
I'm using all of these. So one of the let's say observational databases will be built starting from the Survey of Surveys project, which is a project we started 2 years ago, actually 3 years ago, to combine together and rehomogenize and recalibrate all of the spectroscopic surveys. So we will combine all of that together. It will be difficult, but we will also homogenize all of the abundance ratios, temperature, gravity, metallicity, and that will be to pre-select interesting candidates, combined with Gaia and Kepler and TESS and the like.
I see.
So that's the database, yeah.
So we want to use the same observing material, but doing how to say, doing very simultaneously the same analysis for every star, right? But based on the old observing material.
No, actually, we homogenize the catalogs for a pre-selection of candidates. So we don't remeasure the spectra. Okay, so we take the catalogs, study the biases and trends among catalogs and homogenize, select interesting candidates, and then take the spectra and the Gaia data and the Kepler data for the interesting candidates, and then analyze the spectra to look for indicators of binarity, which can be, well, it has been done to a certain extent, but radial velocity variations, emission in the H-alpha line, or for the infrared surveys in the helium chromospheric lines, indicators that the star is a binary somehow. And then once we get our nice stars, then we get the chemistry and we reanalyze with higher resolution spectra. Because if the star is in an interacting binary or if it's rotating fast, then it's distorted, right? And so the classical analysis is not accurate enough. So it's a long way.
I see. Okay. Thank you very much. Very ambitious project.
Yeah. Yes. 5 years are not many. We will see what we can do.
Thank you.
Any more questions? Jan.
No.
Yes, hi. Maybe I missed it, but you showed this anti-correlation with some elements. Is it easily understandable by accretion that the anti-correlation will happen, or like the interaction in binary stars, or just it's a mystery for now?
Not yet, not yet. For example, for some populations, like the S-rich stars, there is the whole field of extrinsic S stars, CH stars, CN stars, where the chemistry has been studied already, and we know that it matches what we see in globular clusters. But for the sodium-oxygen anticorrelation, as far as I know, no binary star, not even the algal types or the types that lose mass and change the chemistry, have been studied from the chemical point of view in all of the elements of interest. So the connection is not established yet, but in principle, conceptually, it is possible. It's just a matter of exploring a bit more and cutting away portions of the parameter space.
And is it not worrying that if, for example, two stars interact and one is dumping material onto another, one could go more depleted, but the other one could go more enriched. But here, all of the stars are like depleted in one.
No. Okay, but okay, imagine this. Imagine a red giant branch star with a hydrogen burning shell, and the bottom of the hydrogen burning shell is activating the sodium, the neon sodium cycle, right? So the chemistry of the neon sodium cycle plus the CNO gives the sodium oxygen anticorrelation if diluted, right? Now, on the surface, this star is identical to its companion. Identical. But when they interact, the companion starts to accrete matter, right? Maybe a smaller mass star. And it first accretes normal gas. As you go deeper and deeper and deeper, you accrete the strange gas. So a gas with higher sodium and lower oxygen, right? So what happens is that the donor is peeled off and shows the chemistry of the shell, which is like on the top here of this plot. While the accretor has a little bit of this mixed with its envelope, so it's perhaps down here. You see? So you can have with one binary two anomalous stars, one on the equilibrium abundance, so at the top of the anticorrelation, and the other one in between here. You see? So that's the trick. So we have to figure out how to do it, and if it's feasible. And maybe it's wrong. It can happen. So if it's wrong, then at least we have a nice database of well-studied binaries, which is absent from the literature at the moment.
Yeah, a great byproduct.
Yeah, in fact,
worth
a lot
doing.
of work.
Yeah, the project worth doing.
Yeah.
Thank you.
Thank you.
Okay, thank you. Any more questions to Elena? I will ask one, but this is something I mentioned to you already. I'm interested in, if you want to find things which are binary, then spectroscopy is probably one of the means, but also photometry is an obvious one, but also astrometry these days, from Gaia, you can tell things are binary. Well, of course, you're sensitive to different types of binaries with different methods, but then. So my obvious question is, how are you going to employ these time domain observations in astrometry, in photometry, and all the others?
Well, my idea is to put my hands, or let's say the hands of the team, on every possible useful source. So, which means something that we are already used to doing is cross-matching big catalogs, right? Like ZTF, Assassin, Gaia, and later when it will come out, LSST, Kepler, TESS. So cross-match all of these together in this survey of surveys project together with the chemistry. So using everything we have available, but also, and including, for example, the Stetson database, like for about 100 clusters, you have at least 100 epochs, if not 1,000 for all of them, right? So you can do a lot of work on that. And indeed, monitoring has revealed many binaries, monitoring of all kinds, spectroscopy time series, photometry time series, and all of these surveys together. So we will also take our own new observations when it's worth it, but mostly we will use these big databases.
Sure, yeah, and I agree that there is a great wealth of archives. When you combine them together, suddenly you start seeing things.
Yeah, and many in great numbers, so you can do statistics with them.
Cool. Excellent. I don't see any more questions, so thank you, Elena, again for being with us.
Thank you, everyone. Thank you for attending and for inviting me.
Thank you.
Bye.
Thank
Ciao,
you all.
everyone.
Goodbye.
Thank you. Bye.